Okay, I start off with tutorial 2 first, and then we continue on with the lecture. Okay. I hope you had a chance to try it. Alright, question 1. Determine whether the following 4 codes are suitable to be used to differentiate data transmissions from different users for a code division multiple access system. So those are the 4 codes. Alright. In the lecture, I show you 2 methods to do it. Okay. One method is to determine the combined receive signal, and for each receive signal, you find the cross correlation for that particular code. Okay. The other method is to find the cross correlation of the codes. And we say that if the cross correlation of the codes are all 0, that means it's good codes. Okay. The cross correlation is somewhere between 0 to 0.5, then it's moderate codes. And greater than 0.5 is terrible codes, right? Okay, so there were these 2 methods. So the second method is much more reliable in that sense. Second method is much more reliable. So I'm going to use the second method. So we determine the cross correlations between these 4 codes. So 1 and 2, 1 and 3, 1 and 4, 2 and 3, 3 and 4. Okay, so that's a pretty straightforward calculation. So if you do that, with the following table there, those are the cross correlations as you can see here. Okay, so this is 1 and 2, 1 and 3, 1 and 4, 2 and 3, 2 and 4, 1, 3. So when you do the cross correlation between 1 and 2, you go minus 1 times minus 1 times plus 1 becomes minus 1. Minus 1 times minus 1 becomes plus 1. Minus 1 times minus 1 plus 1. Plus 1 times minus 1 becomes minus 1, etc. You add it all together, all 0. Beautiful, nice codes. Okay? Pretty straightforward. Any questions? Okay, next question. Question 2. A pure Aloha system transmits at 16 kilobits per second. Each station on average sends a 512-bit packet every 20 seconds. What is the maximum effective number of stations that the system can accommodate? Alright? So these are exactly the same example that we had during the lecture, except I changed the numbers. Okay? So, first of all, what do we know of this system? We know that the transmission rate is 16. Right? We know that the packet size is 512. And 1 packet every 20 seconds. Lambda is 1 over 20. Okay? That means in 1 second, 1/20th of a packet is sent. Okay? So, Aloha system depends on TTXM, the time it takes to transmit the packet. Okay? So, the time to transmit a packet will be 512 bytes divided by 16 times 10 to the 3. Okay, time to transmit. Alright? And for each station, okay, traffic for each station that's the traffic. Okay? So if you have n stations, And the maximum rate that you can transmit effectively for aloha is 1/2E. We derived that in the lectures. Okay? So the only unknown is n.
Why is it 1 over lambda?
Because you derive it, we differentiated the throughput with respect to lambda. Set it to 0 and found lambda max.
The lambda is the
Okay?
arrival rate.
So that was inside here. Okay? Yeah. We differentiated it and found lambda max. We found S max, and from S max, we found that the maximum carried traffic is 1/2. The maximum effective traffic that is carried is 1/2.
Yeah, but I mean the traffic for each station is lambda times T transmit.
Oh yeah, okay. Lambda, not 1/2 lambda. I don't know. It's not very simple. Yeah, thanks. Yeah, this is lambda. Okay, thanks. Any questions? So that's the method before I bring out the numbers. Okay, so you do that. Get all the numbers here. So it be 114. We take the floor value, floor integer value, 114 stations. Okay, so that's part of it. Any questions?
For the transmission delay, since the channel cannot transmit the signal at the full rate, which is 16 kbps.
Yeah, we'll come to it. That's part C. Okay, that's part C. So you can do the same thing with slotted aloha, which is part B. How many stations can the system accommodate for slotted aloha? So in the case of slotted aloha, the maximum effective traffic that can be carried is 1/E. So again, you plug everything in, so it's slightly double. Okay. Which is this part here. So you can do, you find that n is 229. Okay? Right. The last part. In each case, when the system is fully loaded, what is the average number of attempts required to send a packet successfully? I'm not actually answering your question, but this question is asking, how many times must you try on the average before you succeed? Yeah, okay, right? So, to do this part, we have to determine the probability of success. Okay, so it's kind of like a statistics and probability. You've done this sort of problems before. You know, you have a coin and you toss the coin. Suppose the probability, if it is an unloaded coin, unbiased coin, the probability of head is half, the probability of tail is half, right? But if it's a biased coin, a loaded coin, maybe the probability of head is higher. So suppose the probability of head is 0.75. That is much more frequent you get head. So how many times must you throw a coin to get a head? 1/0.75, right? Agree? So this is how it is. So now, if you know the probability of success, which we can calculate which you can see from here, is P naught, probability of success. So if I can calculate P naught, then I can calculate on the average how many times must I try, because it's 1 over P naught. Okay? Huh? So that's part C. Any question? So that's your PO, P naught, based on the maximum lambda max. So you plug it in, you can calculate P naught is 1 over E. So the average number of transmissions will be the reciprocal of P naught, which is 2.78. Now it turns out it's the same number of retries, whether it's pure aloha or sorted aloha. Okay, same number of retries. Both are 2.718. Okay? Any questions? I've already uploaded tutorial 1's answers. Okay? Yeah. No questions? Let me go to question 3. This is more descriptive. What are the relative advantages and disadvantages of persistent and non-persistent CSMA? Yes? CSMA is carrier sense multiple access. You listen before you send. Alright? And then the persistent tells you the sending protocol. Okay? So just to recap, this persistent CSMA means that if I've got packet I send, I listen. If it's idle, I send. If the channel is busy, I keep listening. Free, then I send. That's persistent. That's why I call persistent. Wait, then go. Okay? Non-persistent is done with a certain probability. Right? I listen. Busy, then I wait. Go, back off. Listen, if it's idle, I have a certain probability of sending. Okay, that's non-persistent. Got it? Okay? So if you think about it, the persistent guy is very greedy, right? Because he's waiting and waiting until the channel is free, and then he sends. What happens if there are more than one guy doing the same thing? They will never succeed, right? Right? They will never, because they will keep banging each other, right? If there's more than one guy. So persistent CSMA is not very good when the system is loaded, because it becomes catastrophic. Okay? So it's only okay if the system is very lightly loaded, persistent CSMA. Agree? Okay. On the other hand, when it's lightly loaded, because it's listening to the channel all the time, and once it's free, it's sent, on the average, his latency will be lower. Because he's monitoring the channel all the time, right? His latency will be lower. But it only works when the system is lightly loaded. Okay, what about non-persistent? Because non-persistent has this probability, the chances of collision is reduced when it's loaded. So if the system is loaded, if the network is loaded, non-persistent will perform better than persistent because it's a little bit more gracious. Alright? But what's the disadvantage? Because he has to throw a dice, he has to get a certain probability to send. So even when the network is slightly loaded, his latency on the average will be higher than persistent. Because you cannot guarantee you will succeed in getting the permission to send on the first attempt. because of the probability. Okay? So in case of non-persistent, all right, it performs better than persistent in a heavily loaded situation, but on the average, non-persistent will have higher latency, higher delay, because of the probability. Okay? Huh? Make sense? Alright, okay. So again, I'm not going to read all this again. It's all summarized here. Okay? Huh? Right, but that's the basic idea. Huh? Alright. Okay, question 4. Also a descriptive one. What are the relative advantages and disadvantages of basic CSMA and CSMA with RTS, CDS? Okay, I haven't covered this yet. I'm supposed to do it today. So I'll leave that alone first. Alright, so question 4 and question 5, I can't do it today. Alright, I'll leave it alone first. Okay, because we haven't covered it. Alright, we are a little bit behind in terms of covering the content. I am getting a bit worried about that. Okay, so what I think we can do is that I won't go into details about all the industry standards because I won't have enough time. Okay, but I will just kind of give you the highlights of the different industry standards. In any case, the industry standards are based on the protocols that we are describing right now, okay, or variations of those protocols. Okay, content will be there. So for example, like our Mac, Media Access Control chapter, 82 slides, you know. 82 slides normally will take 3 hours. Alright, and then after that I have to do routing protocol. I actually added content when I was revising it before the semester started. That one, I added another 20 slides, which I know I cannot finish. Okay, so I will just do the highlights in that case because the details are in the notes. So unless there's something you want to discuss later, when you look at it and you don't understand, then we can do it during the tutorial part of the sessions. Okay? Because I have to give up this class after recess. Because Prof. Tam is going to come in. Okay? Right? Now, so I'm going to leave 4 and 5 first because I haven't covered RTS, CTS yet. Okay. The other announcement that I have, I don't know if everybody's here yet, is I think the, have I told you the exam venue yet? You know the exam date, right? Yeah. I think we might have, let me check after so I'll tell you whether we have the exam venue. Okay. I'm still struggling. Let me see, have I got your? There are about 50 plus of you here in this class, if I'm not mistaken. Okay, if I'm not mistaken. 58 students. Which I think we can do our quiz here. We just separate you guys out. That's all. So we don't have to go elsewhere. Alright? We don't have to go elsewhere. I just need to confirm with Prof. Tam whether you will do it on week 7 or week 8, that's all. Alright? But don't worry, on the day of the quiz, I will start at 6 because I know it's impossible for some of you to get here by 6. Alright? We will probably start at either 6:30 or 7. Alright, so then you should have enough time to get into campus for those who are, particularly for those of you who are working. Okay, we won't start at 6. Okay, it's just I just need to confirm whether it's week 7 or week 8. So I will send out an email notice to all of you with all these details. Okay, is that fine? Okay, and the coverage will be whatever I have done up to week 6. Okay, which is basically the basics of wireless network protocols. Okay, this is what that, let me jump to the lecture. Okay, and this is where I stopped last lesson. Right? I told you about the hidden node problem and the exposed node problem. Yeah? Okay? So in the hidden node problem, we have A here, B here, and C here. A and B can hear each other. B and C can hear each other, but A and C cannot hear each other. So both of them want to send data to B. But because they cannot hear each other, they may send it at the same time and there's a collision. Alright, that's the hidden node problem. Okay? In the exposed node problem, we have A, B, C, and D. Okay? Alright? This guy is talking to these two guys. Let's say this guy is talking to this guy. Okay? This guy is talking to this guy. Of course, he can hear it because it's within range. But this guy is outside the range. So although he's talking to him, alright, and he wants to send data to him. Okay, wants to send the data to him. But because he can hear him, he's very obedient. He keep quiet. But actually he can send because it will not affect transmission over there. That's the exposed node problem. Got it? He sending him. He want to send to him, but he heard his transmission. So he keep quiet.
If the third one sent the
Cannot. He cannot send. He heard him what? He heard him sending to him. So he has to behave.
So this is correct.
Huh? He behave, correct behave. But actually he can send to him. He wants to send to him, not to him.
But if at the same frequency, it will be.
No problem. He said because his signal will not reach there.
Yeah.
No problem. Right? His signal can reach here, but it's okay. He's a sender, it's not a receiver. He's sending to him. His signal cannot reach there. Okay, so that's called the exposed node problem. So we have a scheme here to deal with these two. Alright? Alright. A couple of methods. One is the busy tone method. Again, there's a lot of words there. Let me just simplify it. Busy tone method basically has a separate busy tone channel. Okay, a separate. So you have the data channel, data packet channel where you actually send the data. And there's a control channel which is a busy tone. You just send a tone. Okay? The earliest version of this is that when a node starts to receive packets destined for it, it emits a busy tone. Okay, so T sending data to him. So since he's releasing data, he sends out a busy tone on this separate channel. Okay, on separate channel. Say, busy tone. So with that tone, people around him will know that he's a recipient. And they will not send anything that will corrupt or collide with this packet. It's a very simple concept. Okay? So that's what it is. Alright? So this is in the boot 2. When a node starts to receive packet destined for it, that means he is the receiver, the destination. It emits an unmodulated tone in the control channel and ends when the packet reception is finished. So a node that wishes to transmit a packet first senses the control channel for the presence of the busy tone. If heard, the node will back off. Okay? If not, the node starts packet transmission on the data channel. So that's basically it. So it solves the hidden node problem and the exposed node problem at the same time. Alright, but of course you need to have another radio, right, for the extra busy tone channel. And there are variations of this. Okay? So the paper is the one written at the bottom there. Okay, very old paper. Alright? Now obviously, the range of the busy tone should be similar to the range of the data channel. All right, otherwise it will be a mismatch. Okay, it shouldn't be shorter, nor should it be longer than the data channel. All right, let's see. Okay, the next one is called the multiple access with collision avoidance for wireless, or MACOR algorithm. Okay, the original one is MACA only, with collision avoidance, without the W. Okay, and it uses this thing called RTS, CTS, DS, data and F. And then there are variations of that. The simplest variation is RTS, CTS, data and F. That's the simplest variation. Okay, what are all these guys? RTS means request to send. CTS means clear to send. Okay, let me describe the simplest version first. Okay, again same. A want to talk to B. You want to send to the other. So A said, request to send. This one here. Okay, clear to send. That means now they have already established a handshake already. Then you will send the data. After you send the data, you will send an acknowledgement. That's the basic. Now, what's the implication of that? Okay, that's it. He wants to send to him RTS. Now, when he sent the RTS, this guy also heard the RTS, which means that he should not send anything, even though he might have data now. Otherwise, there will be problem. Okay? So, anyone who hears this RTS, CTS in that neighborhood will defer their transmission. In addition, in the RTS, it will tell its neighbors how much data he wants to send. So you can expect to be delayed for this amount of time. You wait for that minimum time. Because I tell you how big is my packet, and I know the data rate. Given the data rate, that means you should be quiet for that minimum duration, right? You can calculate that out. Okay? You can calculate that out. So the size of the data packet is usually included in the RTS message. Okay? Right. Now, the variation to this is the RTS, CTS, DS. We added the DS. DS means data sending. Alright? So, I say RTS. Then you send back the CTS. Then I send DS. Okay? DS is like kind of a reconfirmation to tell the people around here that I'm going to start sending data now. Okay? And the size of that data is inside the DS as well. Okay? So this is a little bit more pessimistic or cautious approach. Alright? Then you send the data and then the acknowledgement. You got the idea? Yeah? Okay? So the diagram inside here is to describe what happens when you go through this RTS, CTS, DS data acknowledgement, plus the reactions of the neighbors. Okay? So in this example, A wants to send to B. You can see, number one, send RTS to B. Okay? You can see here. A wants to send to B. So, request to send. Now when he sends the request to send, of course E and F will overhear that, right? E and F will overhear that. And they should then defer their any transmission. Then B will respond with a CTS. Now when B responds with a CTS, obviously C and E can overhear because they are neighbors. Which means that again, E will defer. Similarly for C, because C heard the CTS. Alright? Now, after that, A will send the DS, which is again overheard by these two guys, which again they will wait. And after the DS, he will send the data. Alright? After he send the data, CTS will send the acknowledgement. I heard the acknowledgement. This guy here heard the acknowledgement. This guy heard the acknowledgement. Okay, this guy don't hear the because it's too far away. But he got the DS, you see. So he knows how long to wait if he wants to attempt something later. You got it? Huh? He knows how long to wait. Okay? Alright? So all the steps are indicated here in terms of step 1 all the way to step number 12. Okay, but I haven't done step 12 yet because that is a variation of RTS, CTS, DS, data, and ACK. Okay? Now this RTS, CTS, DS, and ACK solves the hidden node problem. But it does not solve the exposed node problem. Okay? Solves the hidden node, but not the exposed node. Okay? Using the same example, tell you why it doesn't solve it. So, D actually wanted to send data to C. D wanted to send it, doesn't. But because C overheard the CTS, he doesn't know where D is. So he keep quiet lah. You know, D sent the CTS, but I heard a CTS, so I better keep quiet. But if D want to send to C, actually can send at the same time because it will not interfere with the others, because it's so far away. It's on the other side, right? Okay, so that's why the exposed problem is not solved. You follow the sequence of things here? It's not solved. Alright? So although things are happening on this side of the network, even in spite of C having heard the CTS, theoretically, D could have sent the data to C because it doesn't interfere with everything on this side of the network. Alright? Okay? So that's the exposed. Let me get my mouse. I like a colorful mouse because I keep using the mouse. So at least I can see where it is. The black ones always keep off. Alright. So this part of the network is busy, yes, but he could have sent data to you because it wasn't okay. Alright, so how do we solve this problem? Okay, I'm not going to discuss because I already described it with all my hand waving just now. Okay, this is just to describe the steps 1, 2, 3 and so on, and the neighbors and how they react. Okay, so one way to overcome the exposed node problem is to find earlier opportunities for D to initiate the entire cycle of RTS-CTS. Alright? So in the previous case, D sent an RTS to C, but C kept quiet. So D has to try again later. Okay? So we introduce a new message called RRTS. Okay? RRTS. Request for RTS. That's RRTS. Request for RTS. RRTS. Okay? So what happens here is that C is aware of all these things going on, right? Okay, this one is side. C is all the things going on here, right? D wants to send to B, right? D sent the RTS, but he knows that I cannot send anything in case I disturb it. But because I'm closer to the action, I can find an opportunity, a window in between all this, and quickly send out a return to RTS to D. So now D doesn't have to wait a long time with the backup to initiate it, because D here got an RRTS somewhere in between this cycle of events that C has sent to it. Alright, and as a result of that, the RTS from D can start earlier to initiate the CTS. Okay, and that's what is happening here. So it's all described inside here. Inside this diagram. So, to increase the node fairness, okay, McCall, which is the name of this protocol, introduce requests for RTS, if you like. RRTS. Okay? So when C cannot reply earlier, due to the ongoing transmissions between A and D, it sends an RRTS to D during the next contention period, somewhere in between some of these managers. Alright? So D immediately responds. When he hears the RTS, he doesn't have to have a long back off now. Okay? D immediately sends the RTS, and normal message exchange begins between D and C. Alright? The other notes that over here, the RRTS will of course differ. Alright? So it is a slotted system, it differ for at least 2 time slots. Okay? So that when they wake up or when they randomly wake up, they can then try whatever they want to do. Okay? So this is the RTS. And the details is in this page. So, if you, all right, that's the details of that paper. I didn't give you the original copy. All right. So this is what it is. So, still quite an old protocol. So the RTS CTS protocol is adopted inside Wi-Fi. Wi-Fi uses that protocol. Okay? Alright? But it doesn't adopt this McCall with the RRTS and so on. It just adopts the basic RTS CTS data protocol.
How is this fair? Suppose A decides he wants to use the resources for a long time.
No. You see, you can only send one packet at a time, so you have to reinitiate an RTS and TCS the next packet you send. You cannot hog the channel. Okay? You cannot hog the channel. Yeah. Alright, so as I said, Wi-Fi uses the RTS CTS protocol. Okay? Which is why, maybe I don't know what I should say now. You know now, if you go to any of the electronic shop where they sell all these IT products, whether it's Challenger or Best or you go to Simlim Square, right? They're pushing a lot of the wireless mesh Wi-Fi routers, right? You don't buy one, you buy 2, right? Very smart, no? Buy one, buy 2 lah. Okay, and then you can wireless mesh them such that if you live in an apartment or condo with multiple levels, you can put one on each and then it will multi-hop to your set-top box. Right? Okay? I don't like that. Because of the RTS CTS. So if you're doing very high-speed streaming, it has an impact. High-speed streaming. Okay? Because you're sending to one intermediate node, that's an RTS CTS there. And then you send another to the set-top box, the base, right? Another RTS CTS. Alright? Okay, so it's not, it has an impact on performance. Alright? But unless you have a very large family, I guess the impact is not so great. Okay, so I'm not going to cover all this. So these are all variations. These are all variations of the busy tone schemes, reservation schemes, schemes that are power aware and energy aware. All right, and so on. Okay, I think on luminous. Okay, if we go to the files, there, I have a whole bunch of papers inside here. If you really love to read all this, okay, FYI only, huh? Okay, and because also I cannot really go into great detail. I mean, most of these papers, if you go into great detail, it can take 1 hour. Okay. So you are welcome to it. All right. At the same time, whatever I found in terms of videos, or some of these schemes are also there. So help yourself to it. Most of these videos are very short, typically 5 to 10 minutes. All right, most of them. Okay. Okay, with that, I more or less covered the basic protocols. All right, I'm going to divert a little bit to personal area networks and some of the standards in this. I won't spend too much time on this, okay, because you can always dig up more material. Okay, so the earliest version of this in terms of the standard was Bluetooth. Okay, Bluetooth. And initially to replace your RS-232 serial cable, okay, in the old days, all right? But then it has evolved, all right, over time, okay, and there are different standards, versions of these standards, which I will show you afterwards. All right, so you have the medium rate, which is 802. Basically, it's 802.15. All right, the medium rate is .1, the high rate is .3, the low rate is .4. Okay, .4 is where Bluetooth and Zigbee split. Okay, I'll show you afterwards. Okay, all right. So, where does the name come from? It came from a anglicized, this English version of a Scandinavian name of this guy, Harold Bluetooth. Okay, there's a historical background behind. All right, it's supposed to be a communication system that unifies the communications. Okay, it uses a fast frequency hopping method. It has adaptive power output. All right, fast acknowledgements, okay, flexible packet types, uses this protocol called continuously variable slope delta modulation, okay. I do not know if you know what is delta modulation. It's a very old technology, all right, that is used to digitize signals. Okay. But it's pretty robust. I'm not sure it's still being used now because there are better standards for this. Basically, for Bluetooth, you can set up what is called a PicoNet, up to 8 devices. One of them is the master, and the rest is slaves. 8 devices. Okay, in one PicoNet. All right. It uses a single channel. It shares the same channel. Okay. So this is a summary of all the things that have happened since 2002. So you see Bluetooth low energy 4.0 version 4. Okay, PME. All right, so that was 8 years ago, 2010. All right, the latest now is version 5, 2 years ago. All right. So most of the devices, the new devices, they are all using BLE now to save energy. Okay, all right. Security has improved quite substantially over the years. Okay. The most common use of Bluetooth now, what is your wireless headset? Most common, right? Okay. Again, these are details which I won't go, you can enjoy yourself. These are on the physical layer. Okay, and then on the protocol stack, the main three are these three. The service discovery protocol, the link layer control adaptation protocol, the logical link control adaptation protocol, and the link manager protocol. So this is to coordinate everything. Okay, that's why after you set up your Bluetooth with your phone, whenever you turn on your earphone, you don't have to reset it again because it's all coordinated by these guys. All right, all coordinated by these guys. All right. Okay, next one is Zigbee. Zigbee is a variation of 802.15.4. Okay, it's a variation of that. So although they come from the same family, Zigbee was intended to be the ultra low cost version. Okay, So as a result, there are some compromises, particularly in speed, okay, and range, okay, because low cost. So it's driven by the ZigBee Alliance that was established in 2002. That actually was conceived in 98, so it's not that young, 98, 20 years ago. All right. So data rate is up to about 250, as you can see here, up to about 250. Make it bigger. Huh? Okay, 250 kilobits per second. All right. Okay, but there are even lower rates version. 250 is at the 2.5 gigahertz ISM band, which is the same as the Wi-Fi. 2.4. But there are other bands like the 864 megahertz in Europe, which only goes at 20 kilobits per second, and the 915 in North America and Australia, which goes at 40 kilobits. Okay, you can choose up to 16 different 5 megahertz channels within 2.4 gigahertz band, which is the iSense band. There is some overlap, but not all of it overlaps with the 802.11 channels. All right, it has sleep, active and sleep modes. That means when it is not doing something, it goes to sleep. So that's the same power, same energy. Okay. You want more information? You can go to this couple of websites.
This is not successful.
That's ZigBee.
It's not successful.
Huh?
This product is not really successful. I've never heard about it.
No, it was quite common before BLE came.
Okay.
Okay, BLE seems to have overtaken it now. Okay, BLE. Yeah. So like a lot of those little sensors that we have, they all use the ZigBee protocol. What we call MODES, MODES, MODES. Prof Tam will talk about it because he's doing the sensor network part. MODES. A lot of them are using ZigBee. Okay. So it comprises of 3 classes of devices. Okay, the ZigBee coordinator. All right, this forms the root of the network. Then you have the ZigBee router. Router is to relay information to the coordinator, and the end device itself. Okay, 3 parts. And then the protocol stack is here. The 802.15.4 is here. But the Alliance has added additional things to make it more user-friendly up here. Okay, which is not part of the IEEE 802.15.4 standard. Okay, so I won't go through the details of the protocol stack. Excuse me. You have the physical layer, 3 frequency bands as you saw earlier, the 2.4, the 800 and the 900 megahertz band depending on the country. It does energy detection, so as to conserve energy. All right. And then it does channel assessment to assess the quality of the channel. So the MAC layer uses CSMA-CA. You know what CSMA-CA is? Listen before you send with a certain deferment. Okay, CSMA-CA. All right. And it can operate either in the beacon or the non-beacon mode. Okay. It takes care of all these different things. All right. And it provides some standard security features for access. So there's the network and security layer, provide you with the security part, and the application support layer over here, which is this guy over here, application support layer, as you can see here. Okay, and that talks to the application objects over here. All right, and then you have device objects over here. That means basically the device objects provides you the profile of the type of devices. So the Alliance have a whole library of different devices. Okay. Then this is the application framework, which I already mentioned. You have the device objects over here, and the application profiles, and the interfaces between that talk to each other. Okay, so that's basically the key. Now, more recent is LoRa, long range. Okay, so it's developed, as you can see, as recently as 2012. So it's quite a young protocol. started in France, intended for long range, up to 10 kilometers. Contains two parts, the physical part and the MAC part, the WAN part, the MAC part, multiple access protocol part. Okay, again, those are the details. There's a short video also, if you go to the Luminous, you can pick it up. Okay, which also explains about these two physical and WAN protocol. So it is not a international standard that has come out from the standards bodies like IEEE or ISO or something. It basically came from this company. Alright, came from this company. Recognizing its potential as a communication protocol for Internet of Things. Okay? Right. So you have gateways so that allow you to, from the device to talk to the gateway to the internet, for example. Okay. Physical layer allows signal hop between end device and one or more gateways. Bidirectional traffic. You can see data rate is very low, 0.3 kilobits per second to 50 kilobits. Using frequency hopping. Alright, again, and there's a data rate setting because it depends on the quality of the channel. So together they have a virtual channel that gives you a certain rate and a certain hopping code. Okay, that's LoRa. So it does have some security mechanisms in place. It uses 128-bit encryption key, session key, network session key, as well as an application session key. Okay, the schematic is this guy here. All right, so those are the application and the network encryption. Okay, simple modulation scheme, frequency shift key. Again, they define different classes of devices, three classes, class A, class B, and class C. Class A is lowest power, bidirectional. Class B is bidirectional with deterministic latency. That means there's some scheduling on slots, so it's deterministic. And class C has the lowest delay, but it also means that it is awake a lot of the time, so it consumes more power. That's class C. All right. Finally, we have Sigfox, again, very recent guy. 2009. All right. In French. All right. Operates at the lower ISM bands. By the way, this 868 and 902, these are the ISM bands when we used to have analog cordless phone. You remember analog cordless phone? Most of you may not see a cordless phone because you grew up as a digital native with smartphones. Right, but in the old days, we used to have a wire there in the house, right? But we put a cordless phone so that you can go all over the house with the headset, right? Okay, so the earlier versions of cordless phone, they use these channels, this spectrum. Okay, this spectrum. Okay, so this is the modulation scheme that it uses, DPSK. All right. And again, there are videos of this that tells you in detail how this modulation scheme works if you're interested in the digital communications part. I won't go into that. So it's inside here, this link. Okay, but it has very small packets. It has a overhead of 12 bytes. 12 bytes of data, and the rest, the other 14 bytes of overhead. Okay, so the data packets are all very small. Okay, and the target market was for IoT, where you don't have to send data too often for IoT. Okay, right. So it's all one hop, based on one hop star topology. So it requires a mobile operator to carry the generated data. Okay. So finally, we come to 802.11. Okay. So the question now in the market is, Where is all this going to play out in the next few years? What's the business model behind it? Nobody knows yet. You know? How are we going to price it? For Sigfox, they price by per packet you send. Per packet that you send. Okay? LoRa, I'm not very sure. Because it overlaps with Zigbee and Bluetooth as well. Okay? Right. Okay, anyway, coming back to Wi-Fi. Wi-Fi is a short form for wireless fidelity. Wi-Fi. Just like hi-fi. Hi-fi, audio hi-fi, right? It's high fidelity. Okay? There is an alliance called the Wi-Fi.org. Okay? And 802.11 is the set of standards under this umbrella. Okay? Alright, originally started back in 97, okay, as a standard, and was at 1 and 2 megabits. Then you have newer versions. I'll show you the whole list afterwards. And it is license exempt. What that means is that you don't have to pay for the IP. Okay? Some companies, they have IP in their products, so we all consumers will have to pay. And it's packaged into the cost of the product. Okay? But of course, we have vendors who also steal IP. Huh? Okay? iPhone for some. Okay, now there's a big battle about Huawei, right? You know that, right? Okay, so it uses CDMA, right? We talk about CDMA, all right? And more advanced versions of that. Originally, we have 3 types of physical layers. One using a direct sequence space spectrum. That means you use the code direct sequence. The other one is frequency hopping. And there's one earlier version of it that uses some sort of infrared, but that one never really made an impact on the market. It supports multiple priorities, supports time critical and data traffic, and power management, and allows a node to go soft. Right, now you have the list of all the standards. Alright, 897, 802.11, 11C, we never saw it. Alright, 11, 11F, A, B, G, we never see DOC, we never saw CD in the market. Okay? All the ones in yellow highlighted are the ones that are in the market that we are familiar with. And okay, see all the amendments. So we never saw all of these alphabets. And AC. That's the latest. Okay? Alright, and there will be others. Okay, what data rates are we expecting? 11A is 6 to 54 megabits. The original one was, but somehow A, for some reason, when it reached market, B came up before A. B came up before A. Alright? Why? Partly because A is in the 5 gigahertz band. So it's at a higher frequency band, which means the electronics is much more expensive. Okay? That's why B came up first. Because it's also lower 2.4 gigahertz band. So things were cheaper. Alright? Okay. So 11B is the one that is the oldest in terms of market presence. Okay? So that one goes all the way to 11 megabits per second. So G is up to 54, N is up to 600, and AC is up to 1.3 gigabits per second. So now if you buy those high-end Wi-Fi router, you know, with 6 antennas, you know this one? Very, very masculine type of antennas. Then you will have all these. Alright? Okay. Yeah.
What's the reason that other technology is not in the market? They are not.
No, some of that is not, to say not there. They are substandards in terms of security or some other improvement that's internal to it. Okay? All right, internal delay. So, for example, let me give you one now. I don't know whether it's listed here. Okay, P. 802.11p is what is proposed for vehicle to vehicle and vehicle to infrastructure communication. But it hasn't really taken off yet.
The theory is it mature?
It is. There are products out in the market. They don't call it 11p. They call it Dedicated Short Range Communication System, DSRC. Okay, DSRC. So we actually had a test bed here, which has been decommissioned. We had a test bed that we ran for about 2 years. We just decommissioned it end of last year. Okay, so in that test bed, we set up something like about 10 or 11 DSRC base stations across the campus. Okay, and that network was used for our shuttle bus onboard Wi-Fi. If I don't know, if you were here last semester, you would still be receiving that service. Earlier part of last semester, if you went on board the US shuttle bus, you will find that your Wi-Fi will automatically be configured. But now that has been decommissioned already because the pilot is over. So in that network, the DSRC, which is based on 802.11p, whenever the bus gets near enough to one of the base stations,